Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is Ohm's Law as applied to AC circuit analysis. Our objective is to examine the fundamental cause and effect relationship of electrical properties known as Ohm's Law. We'll examine how phasor equivalents and complex impedances are employed in calculation of voltage, current, and impedance for AC circuits. This lecture operates under the presumption the viewer has more than a passing familiarity with representing electrical phenomena as phasor equivalents, as illustrated in the phasor notation lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, only dimly recall its contents, please take the time to do so now. Additionally, it's presumed the viewer is capable of representing resistors, capacitors, and inductors as complex impedances. Alright folks, this is it. This is the moment you've been waiting for. This is the one lecture which ties together all that complex number math, impedance calculation, and phasor equivalent baggage we've been dragging around with us for the past couple weeks and puts it to use. Without underestimating its importance, a thorough understanding of Ohm's Law is an absolute necessity for AC circuit analysis. Try not to screw it up. As profoundly important as Ohm's Law is, it's not that hard. When applied to AC circuit analysis, Ohm's Law is almost a direct copy of our previous experience with DC circuit analysis scenarios. Take the term resistance, swap it out for the term impedance, add some complex numbers, and call it good. If you take a step back, you'll realize it really is that simple. And if you've already got an understanding of Ohm's Law as applied to DC circuit analysis scenarios, you'll probably do just fine. The new dimension added to Ohm's Law to AC circuit analysis using phasors brings to the table is magnitude and direction. This implies that the incorporation of reactive elements like capacitors and inductors in AC circuits will include phase-shifted effects that can be accounted for using phasor representation. Allow me to demonstrate. Let's examine the magnitude relationship first, a concept you should be readily familiar with by now. Given constant opposition and increased cause, effects should increase. Conversely, given constant opposition and decreased cause, effects should decrease. Coming at this from a different angle, given constant cause and increased opposition, effects should decrease. Finally, given constant cause and decreased opposition, effects should increase. This cause, opposition, and effect relationship should make sense as numerous phenomena follow this basic pattern. Consider your performance, or lack thereof, in basic electronics. If you put a lot of effort into it, i.e. your cause is high, and have a quiet, calm, and supportive study environment, i.e. your opposition is low, most likely you'll succeed. If, however, you put minimum effort into your studies, i.e. your cause is low, and the neighborhood raccoon has built a nest out of your shredded textbook and notes, i.e. your opposition is high, most likely you won't succeed. Now simply apply this understanding to electrical phenomenon. Voltage is the cause of charge movement. Resistance, or in our case impedance, is opposition to current flow. Current, the movement of charge, is the effect. Given constant impedance and increased voltage, current should increase. Conversely, given constant impedance and decreased voltage, current should decrease. Coming at this from a different angle, given constant voltage and increased impedance, current should decrease. Finally, given constant voltage and decreased impedance, current should increase. This should not be new to you, and if it is, I'm sending you all the way back to Basic Electronics 1 to begin anew. Look me up in 12 to 15 weeks once you've got this concept down. The twist Ohm's Law as applied to AC circuits brings to analysis scenarios is that using complex impedances and phasors, including both in magnitude and direction, accounts for phase-shifted effects inherent in reactive elements like capacitors and inductors. If DC Ohm's Law can be represented as the three-variable relationship of voltage V, current I, and resistance R, our AC equivalent can likewise be represented as a three-variable relationship of voltage V, current I, and impedance Z. Note V and I are phasor quantities defined by an effective value and phase shift, and impedance similarly includes magnitude and direction. Three permutations of Ohm's Law demonstrate that current equals voltage over impedance, voltage equals current times impedance, and finally impedance equals voltage over current. Let's examine a phase-shifted response on a general level before we bring numbers into the picture. Recall that resistors are not reactive elements and dissipate all energy supplied to them in the form of heat. It makes sense then that resultant current through a resistor will be perfectly in phase with the voltage across it. When no current flows through the resistor, there will be no voltage drop across it. If maximum current flows through the resistor, top to bottom, there will be a maximum voltage drop across it, positive to negative, top to bottom. Again, when no current flows through the resistor, there will be no voltage drop across it. If maximum current flows through the resistor, bottom to top, there will be a maximum voltage drop across it, positive to negative, bottom to top. In summary, current through a resistor will always be in phase with the voltage across it. Capacitors and inductors, however, are reactive elements and can momentarily store and discharge energy. This necessitates more detailed inspection. On a very general level, we can divide circuit elements into two general classes, passive and active elements, where reactive elements, like capacitors and inductors, have a foot in both worlds. A passive element, like a resistor, follows our previous observations. When current is traveling through a passive element, top to bottom, that element will experience a voltage drop positive to negative, top to bottom. Conversely, when current is traveling through a passive element bottom to top, that element will experience a voltage drop positive to negative, bottom to top. An active element, like a sinusoidal AC voltage source, is entirely different in nature. When the active source establishes a voltage differential positive to negative, top to bottom, current would emanate from it, traveling out of the positive top terminal and return to the negative bottom terminal. Conversely, in the bottom half of the sinusoidal cycle, an active source would establish a voltage differential positive to negative, bottom to top. Current would emanate from it, traveling out of the positive bottom terminal and return to the negative top terminal. This is completely opposite to our observations regarding passive elements. Reactive elements, like capacitors and inductors, periodically alternate being passive and active elements, and as such there exists a phase shift between voltage and current. Allow me to demonstrate. Let's deal with capacitors first. Consider a capacitor during a cyclical charge and discharge process. Current flows into the capacitor, top to bottom, and an increasing voltage differential develops across the capacitor, positive to negative, top to bottom. In this sense, the capacitor is acting just like a passive element, absorbing energy. When a given voltage potential has been reached, the capacitor then begins the discharge process. During discharge, current would flow out of the capacitor, top positive terminal. However, a decreasing voltage differential is still experienced across the capacitor, positive to negative, top to bottom. In this sense, the capacitor is acting just like an active element, supplying energy. The other half of a sinusoidal cycle would be a repeat of the previous process, only polarity is swapped. During the charging process, current would flow into the capacitor bottom to top, and an increasing voltage differential would develop across the capacitor, positive to negative, bottom to top. Again, in this sense, the capacitor is acting just like a passive element, absorbing energy. When a given voltage potential has been reached, the capacitor would then begin the discharge process. Current would flow out of the capacitor bottom positive terminal. However, a decreasing voltage differential is still experienced across the capacitor, positive to negative, bottom to top. In this sense, the capacitor is again acting just like an active element, supplying energy. Given this cyclical charge and discharge process, it could be said that current through a capacitor would always lead the voltage across it by 90 degrees. It also can be rightly said that voltage lags current by 90 degrees, although I prefer the prior observation. Current through a capacitor always leads voltage across it by 90 degrees. When the capacitor is uncharged, i.e. has no differential across it, current rushes in and is respectively large in magnitude. During the charge process, an increasing voltage differential develops across it and current subsides. When charged, i.e. has a large differential across it, current stops. When discharging, current flow reverses direction and the voltage differential drops. When completely discharged in one direction, the charge process begins anew, only in the opposite direction. When uncharged, i.e. has no differential across it, current rushes in and is respectively large in magnitude. During the charge process, an increasing voltage differential develops across the capacitor and current subsides. When charged, i.e. as a large differential across it, current stops. When discharging, current flow reverses direction and the voltage differential drops. When completely discharged in one direction, the charge process begins anew, only in the opposite direction. We're right back where we started. In summary, current through a purely capacitive element will always lead voltage across it by 90 degrees. Inductors also exhibit alternating periods of active and passive behavior. Allow me to demonstrate. Consider an inductor in the process of cyclically expanding and collapsing the magnetic field. Experiencing increasing current, the expanding magnetic field generates a voltage differential across the inductor, positive to negative, top to bottom. In this sense, the inductor is acting just like a passive element, absorbing energy. Experiencing a decrease in current, the collapsing magnetic field continues to push current out of the bottom terminal by generating a voltage differential across the inductor, positive to negative, bottom to top. In this sense, the inductor is acting just like an active element, supplying energy. The other half of a sinusoidal cycle would be a repeat of the previous process, only polarity is swapped. Experiencing a reversal and increase in current, the expanding magnetic field would generate a voltage differential across the inductor, positive to negative, bottom to top. In this sense, the inductor is again acting just like a passive element, absorbing energy. Experiencing a decrease in current, the collapsing magnetic field continues to push current out of the top terminal by generating a voltage differential across the inductor, positive to negative, top to bottom. In this sense, the inductor is again acting just like an active element, supplying energy. Given the cyclical expansion and collapse process, it can be said that voltage leads current by 90 degrees for an inductor. However, I prefer phrasing this using a different perspective. Saying voltage across an inductor leads current through it by 90 degrees is equivalent to current lagging voltage by 90 degrees. I'll come back to rephrase this observation in a moment. Using this plot, it can be demonstrated that when current increases, a voltage differential occurs across the inductor. When current is relatively stable and at a positive maximum, no voltage differential occurs across the inductor. When current decreases and reverses, a voltage differential occurs across the inductor. When current is relatively stable and at a negative maximum, no voltage differential occurs across the inductor. When current increases and reverses, a voltage differential occurs across the inductor. We're right back where we started. Note this plot of voltage and current for the inductor uses current as our established reference, since it's easier to initiate discussion about the cyclical interchange in this manner. Using this perspective, it can be said that voltage across an inductor will always lead the current through it by 90 degrees for a purely inductive element. One needn't always use this same perspective. One can also plot current through the inductor using voltage as our established reference. When drawn in this fashion, current appears to be lagging voltage by 90 degrees. Both these observations are true, being merely different ways of saying the same thing. However, I have a tendency to think using the second perspective. Current through an inductor will always lag the voltage across it by 90 degrees. This periodic oscillation between active and passive natures leads to an important distinction between reactive elements like capacitors and inductors and passive elements like resistors. When we look at voltage and current plots for all three elements, resistors, capacitors, and inductors, a couple important observations can be made. Current through a purely resistive element will always be in phase with the voltage across it. In contrast, current through a purely capacitive element will always lead the voltage across it by 90 degrees. Finally, current through a purely inductive element will always lag the voltage across it by 90 degrees. Note all three plots use voltage across the element of interest as our established reference. Remember these important characteristics because they form useful means of checking your work in later exercises. I say again, current through a purely resistive element will always be in phase with the voltage across it. In contrast, current through a purely capacitive element will always lead the voltage across it by 90 degrees. And finally, current through a purely inductive element will always lag the voltage across it by 90 degrees. At risk of blowing your mind, let's talk about AC power. I know this lecture's objective is Ohm's Law, a subject we've yet barely scratched the surface of. but let's briefly discuss AC power before returning to our intended goal. Power, the product of voltage and current, for passive elements like resistors will always be positive, where positive power is defined as power being dissipated by the passive element. Periods of positive voltage times positive current yield a burst of positive power as equally effectively as do periods of negative voltage times negative current yield another burst of positive power. For a single complete cycle of a sinusoidal AC voltage waveform, the resistor would experience 2 bursts of positive power dissipation. Note that 2 bursts of positive power dissipation can be averaged to arrive at an average power dissipation figure over time. We'll return in a moment to discuss the significance of this observation. Power for reactive elements like capacitors and inductors, in contrast, will cyclically alternate between periods of positive and negative power. Given positive power is defined as power being dissipated by the element, negative power can be defined as being supplied by the element. Can you dig what this means? A charging capacitor absorbs energy, and then during the discharge process returns all this stored energy. Similarly, the expanding magnetic field in an inductor would absorb energy, and then when it collapses, return all this stored energy. We'll examine this phenomenon in greater detail in much later lectures, but as a preview, consider a plot of power for both capacitors and inductors subjected to sinusoidal AC voltage. In terms of the capacitor, a period of positive voltage times positive current yields a period of positive power while the capacitor is charging and absorbing energy. A period of positive voltage times negative current yields a period of negative power while the capacitor is discharging and supplying energy. A period of negative voltage times negative current yields another period of positive power while the capacitor charges and absorbs energy. Finally, a period of negative voltage times positive current yields a period of negative power while the capacitor is discharging and supplying energy. As we anticipated, we observe cyclical alterations between positive and negative power, or the passive and active natures of a reactive capacitor. In terms of the inductor, a period of positive voltage times negative current yields a period of negative power when the magnetic field established during the previous cycle collapses and returns energy. A period of positive voltage times positive current yields a period of positive power while the magnetic field in the inductor expands and absorbs energy. A period of negative voltage times positive current yields a period of negative power when the magnetic field collapses and returns energy. Finally, a period of negative voltage times negative current yields another period of positive power while the expanding magnetic field of the inductor builds and absorbs energy. As we anticipated, we observe cyclical alterations between positive and negative power, or the passive and active nature of a reactive inductor. Let's return our attention to the average power dissipated by the resistor. Recall that the 2 bursts of positive power dissipation can be averaged to arrive at an average power dissipation figure over time. Not so for reactive elements like capacitors and inductors. Given equal periods and magnitudes of consumption and supply, it could be rightly said that the average power dissipated by these reactive elements over time is 0. What does this mean in terms of power, given these reactive elements continually draw current? It means power, previously a simple product of voltage and current for DC circuit analysis scenarios, must take into account the phase shift between voltage and current. In summary, AC power is multidimensional in nature and can be thought of in terms of real, reactive, and apparent power, where real power is that amount actually dissipated on average, and reactive power is that amount cyclically exchanged between the source and the reactive elements. Like I said, we'll examine AC power in greater detail in much later lectures, but I just wanted to briefly expose you to this topic as soon as possible. Alright, let's get this lecture back on track and return our discussion to Ohm's Law for AC circuit analysis scenarios. If all this noise about the cyclical alteration between the active and passive natures of reactive elements, the charge and discharge process of capacitors, the expansion and collapse of the magnetic field in inductors, and what current and voltage are doing at every specific point in a sinusoidal AC cycle seems tedious and long-winded, you're not the only one that thinks so. I too grow tired of this ceaseless droning and can comfort myself with our previous guidelines. current through a purely resistive element will always be in phase with the voltage across it. In contrast, current through a purely capacitive element will always lead the voltage across it by 90 degrees. And finally, current through a purely inductive element will always lag the voltage across it by 90 degrees. Is there some way of arriving at these same results without all the time-consuming nonsense? Indeed there is. This technique is Ohm's Law. Recall that AC Ohm's Law is a three-variable relationship of voltage V, current I, and impedance Z. Three permutations of Ohm's Law demonstrate that current equals voltage over impedance, voltage equals current times impedance, and finally impedance equals voltage over current. Note, voltage and current are phasor quantities, and impedance similarly includes both the magnitude and the direction. If one is capable of representing voltage as a phasor equivalent and the impedance of an element as a complex number, one is capable of quickly solving for the resultant current as a phasor equivalent using simple division. Current equals voltage over impedance. Similarly, if one is capable of representing current as a phasor equivalent and the impedance of an element as a complex number, one is capable of quickly solving for the resultant voltage as a phasor equivalent using simple multiplication. Voltage equals current times impedance. Finally, if one is capable of representing both voltage and current as phasor equivalents, one is capable of quickly solving for the resultant complex impedance using simple division. Impedance equals voltage over current. In summary, Ohm's Law works without a lot of confusing discussion or complicated math. The only prerequisite skills you need to bring to the table in advance is an ability to translate smoothly between the time and phasor domain and vice versa, calculate complex impedance, and multiply and divide complex numbers. Techniques by now I hope you've mastered since we've spent the past couple weeks practicing them. Consider a 200 ohm resistor subjected to sinusoidal AC voltage with the following properties. It looks like it has a 170 volt peak value, a period of 16.7 milliseconds corresponding to a frequency of 60 Hz, and it is assumed to be the reference waveform since its phase shifted by 0 degrees. You should be skilled in determining these values from both the time-varying expression as well as the plot of voltage as a function of time. Let's say we were being asked to solve for the current through the resistor in terms of the phasor equivalent, the time-variant current expression I of t, and finally additionally we're being asked to plot current as a function of time. To make use of Ohm's Law to satisfy these demands, we need to establish conditions ideal for its use. First, we need to express voltage as a phasor equivalent. Doing so yields V equals 120 volts at an angle of 0 degrees, where 120 volts is the effective value of sinusoidal AC voltage with a peak of 170 volts, and 0 degrees is the phase shift. Do we really care about frequency? No, not really. Inside the phasor domain, everything is assumed to have a frequency of 60 Hz for this particular problem. Now we need to express the resistance as a complex impedance. Doing so yields Z equals 200 ohms at an angle of 0 degrees. Now, since we're being asked to solve for current, we divide the phasor equivalent voltage V by the complex impedance Z to solve for I, the phasor equivalent current. Doing so yields I equals 600 milliamperes at an angle of 0 degrees, where 600 milliamperes is the effective value of the resultant sinusoidal current, and it is phase shifted by 0 degrees. Additionally, since the above conditions were established at conditions of 60 Hz, it is assumed current also has a frequency of 60 Hz. Note the phasor diagram shows I overlapping V, indicating they are in phase with one another. If we needed to express current as a time-variant sinusoidal expression, I of t would be equal to 848.5 milliamperes times the sine of 360 times 60 times t plus 0 degrees, where 848.5 milliamperes is the peak value of sinusoidal current with an effective value of 600 milliamperes. If we needed to plot current as a function of time on the same graph as voltage, note it is also phase shifted by 0 degrees and appears to be completely in phase with voltage in that it simultaneously peaks and valleys. This result shouldn't be earth-shattering, but it should overjoy you that we never had to resort to time-consuming instantaneous analysis to arrive at these conclusions. The only reason this discussion took so long is because we were being asked to transfer information from the time domain to the phasor domain, perform the calculation, and then transfer the result back to the time domain. Often this game of telephone is unnecessary, since most circuit analysis scenarios are best kept at the level containing only the most pertinent information, notably the phasor equivalent. This Ohm's law manipulation can be most compactly summarized as: given voltage with an effective value of 120 volts across a 200 ohm resistor, one can anticipate current to have an effective value of 600 milliamperes with no phase shift. All pertinent information is immediately recognizable using the phasor equivalence. Let's try the same type of problem, only this time featuring an 8 microfarad capacitor subjected to sinusoidal AC voltage with the following properties. It looks like it has a 339.4 volt peak value and a period of 20 milliseconds, which corresponds to a frequency of 50 Hz. Additionally, this waveform is assumed to be the reference waveform since it's phase shifted by 0 degrees. Let's say we're being asked to solve for the current through the capacitor in terms of the phasor equivalent and the time-varying expression I of t. Additionally, we're being asked to plot current as a function of time. As previously, we need to establish conditions ideal for the use of Ohm's law. First, we need to express voltage as a phasor equivalent. Doing so yields V equals 208 volts at an angle of 0 degrees, where 208 volts is the effective value of sinusoidal voltage with a peak of 339.4 volts, and 0 degrees is the phase shift. Do we care about frequency? No, not really. Again, inside the phasor domain, everything is assumed to have a frequency of 50 Hz for this particular problem. Next, we need to express the capacitor as a complex impedance. Doing so yields Z equals 397.8 ohms at an angle of negative 90 degrees. Note the negative 90 degree direction for the capacitive complex impedance. If you're skilled in the manipulation of complex numbers, as I expect you to be, you should have an idea of what's coming next. Since we're being asked to solve for current, we divide the phasor equivalent voltage V by the complex impedance Z to solve for I, the phasor equivalent current. Doing so yields I equals 603.2 milliamperes at an angle of positive 90 degrees, where 603.2 milliamperes is the effective value of a resultant sinusoidal current and is phase shifted by positive 90 degrees, meaning it's leading our agreed upon reference by 90 degrees. Additionally, since the above conditions were established at 50 Hz, it is assumed current also has a frequency of 50 Hz. Note the phasor diagram shows I leading V by 90 degrees. If we needed to plot current as a function of time in the same graph as voltage, note it is phase shifted by positive 90 degrees. A positive 90 degree phase shift for a waveform with a frequency of 50 Hz, corresponding to a period of 20 milliseconds, is equivalent to a 5 millisecond differential between current and voltage. Again, a lot of this is superfluous information, only serving to obfuscate the most important points. Most circuit analysis scenarios are best kept at the level containing only the most pertinent information, notably the phasor equivalent. This Ohm's law manipulation can be most compactly summarized as: given 50 Hz sinusoidal AC voltage with an effective value of 208 volts across an 8 microfarad capacitor, one can anticipate current to have an effective value of 603.2 milliamperes with a positive 90 degree phase shift. All pertinent information is immediately recognizable and in keeping with our expectations.